last class, the last few lectures, we were discussing about this chain, and we were talking about this baseband modulation. And in that baseband modulation, that we are talking about line coding. So line coding means that these are those line codes are PCM codes. That means line code or PCM. You can remember that I have a bit sequence, and it is that means on and off, means on means some 5 volt, something like that. Then 0 means something like this. That way, say polar is something like that. That polar means bipolar. That means I have +1, and for 0 I have a -1 volt, and all these things. So this is there is a bipolar return to 0. That means I have always it is polar return to 0 and bipolar return to 0. I forgot about the difference of these two. But on-off energy means these are the different codes, so that we discussed, and see if you remember that this one is rather better. Most of the things are. And in this one, basically we'll discuss about this PCM sequence, or sometimes we say it is a line code. Okay, line code. Line code means these are the line code. This is the line code. This is another line code. On these line codes, and we will calculate, and see here we will rather, you see that mostly that all the things, they are something like the pulse nature is something like that rectangle. And we want to little bit generalize this one, and we try to see the power spectral density of this signal. This, because finally you are sending this signal, so you have this one, this bit sequence. If you can see the other one, other picture, that means you have a bit sequence from here, and from there you are sending this type of, say here they have given the generalized kind of thing, but actually we have seen something like this, all pulses type of thing. Say some depending on the nature of the coding, actually coding nature of the modulation, baseband modulation. Now, so that so this one is, please remember, this book is BP Lathi. This book is also available in net. Please download BP Lathi and D. Okay. So digital and analog communication. This is chapter 7 I am teaching. Okay. So this one we'll discuss here about, so that means you understand line coding, and for line coding, which line code you will use. Each line code has its own advantage and disadvantages that we already discussed, that transmission bandwidth, power efficiency, error detection, favorable power spectral density. Because favorable power spectral density means I don't want means zero power spectral density at F equal to 0 because of AC coupling and transformers up. So that is we discussed that near DC I should have a power spectral density should be 0 kind of thing. Okay, and significant power in low frequency component should be avoided because it causes the DC wind. Okay, so that means we have to calculate the power spectral density of each of the line code. That means that we will discuss in this class. That means PSD of the various line codes. Okay, now, and so that means here what we will do. You see that so is the rather context clear? That means we are still in baseband coding. Okay, if you can remember that I have shown you some pictures here. That means the power spectral density, some of the power spectral density figures, spectral attributes of PCM waveforms are discussed. And then I plotted this spectral density. You see that this is the power spectral density. This is the power spectral density. And this power spectral density, how to calculate this power, that I have shown some inefficient, this one I don't want, and all these things. I like to discuss this power spectral density in a detail. Okay, this is the class. Now for that, actually what we are going to do, that we will consider a generic pulse. First of all, not the square pulse or box pulse, it is a generic pulse Pt, whose corresponding Fourier transform is capital P. First of all, and we can denote the line code symbol at k as AK. Okay. Now transmission rate is 1 by TB pulses per second. Please remember, pulses per second. And the line code generates a pulse train constructed from the basic pulses Pt with amplitude AK starting at time t equal to KTB. Okay. Now let us see what do I mean by this. Okay, let me complete this. Then I will show you the picture. That you know these things. Now the kth symbol is transmitted as AK Pt minus KT. That means the k unit delayed. Okay, the kth symbol, that is k unit delayed. There is some generic pulse Pt, and I have a amplitude AK. Okay, so let us see. Means what it is. Let us see the picture. You know these things. I'm sure that I have. Okay. Is like that. Say in this pen, if you can remember, that means when I was doing some sort of a 8-ary pen, then so what was my symbols? 0, 1, 2, that means 3 bits grouped together, and finally we have got some 1, 0. My bit string was like this, and I have made a 3 bits grouped together, and I am doing 8-ary pen, so that's why I have made a 3 bits grouped together, and I was making 5, then 111, then 7, and all these things. And here I am assuming my pulses are some sort of a rectangle. So 5 Pt, 7 Pt minus 1, and Pt is some sort of a something like this. If you remember that Pt is, this is 1, then this is some Tb, bit duration or symbol, whatever you say. It's not just symbol duration, not bit duration. Okay, bit duration is this much. It is 3 symbol duration, Tas rather. So because 101 I am sending by this one. It is 101 is a symbol. Okay. Bit is 1. Okay. So here the next picture says this. Please remember this is the bit duration, but this is the symbol duration. Okay. I am talking about symbol duration. Okay. But they have taken, because just depending on that sequence of ornaments, so rather context we choose the things. Okay. So this is my Pt. Okay. Now what I am doing, that means I can represent this as 5 into Pt plus 7 into Pt minus Ts plus 5 into Pt minus 2 Ts, then plus 2 into Pt minus 3 Ts, something like that. The same thing I am doing with the generic Pt. Okay, that means say I have taken a Pt, something like this. Okay, not, so that means forget about B. Okay, so Tb there, you see that Tb is the pulses per second. Rather I can write as, you need not write B. You just write 1 by T kind of thing. B is generally it is written as a in terms of bit. They have done something. So this is an unnecessary confusion. Anyway, so what I am doing, this is my pulse, and I am doing something like this. I have some bit stream. These bit stream I have grouped together. Finally, I have got some symbols. My symbols are AKs. That means symbols are AKs means in the previous case, symbols are, see, A0 was 5, A1 was 7, A2 was 5, A3 was 2, A4 was 2, A5 is 3, A6 is 2, A7 is 1, something. Now I can do the amplitude something like that. Some may be negative, some may be positive also. So then AKs will be, some AKs will be negative, some AKs may be positive. I can choose the code in such a way. Okay. Say I am saying my codes are minus 4 2 plus 3, something like that. Okay. So I can represent the code in that way. So that means my so first bit is some sort of a sine bit, and next two bits are maybe the actual magnitude bit. Anyway, so they have taken in this way, so that's why some are the negative things. So say some it is some pulse, first symbol into pulse, then second symbol into some pulse delayed pulse, then third symbol into some delayed pulse in this way. So what is my rather? So this is my yt, and this is my that means the output signal that I am transmitting from here. Actually, this yt is what? Yt is basically, if you can remember, this is my yt. This is my. Okay. Now then. So this is my yt, and what I am doing, so rather I am defining this one as, see, I am defining a pseudo filter kind of. What is that? So it is nowhere related to that. This try to understand. I have got the yt. Yt is that pulse. Yt is the pulse. I am assuming, see, I have some xt and I have some filter whose impulse response is pt. That means that is my impulse response. Okay. And I have got the filter output as yt. Okay. This is my own idea. It is actually not there. Now, what is my xt? Xt's are basically some AKs. Okay. Some AKs. That means the symbols. Okay. Some k bits grouped together, and so m equal to 2 to the power k bits grouped together, so MRE symbols. Okay, some amplitude modulation kind. Okay, so then I can write as yt as ak pt minus ktb. Okay, and k is some say minus infinity plus infinity. Okay. Now I am assuming that means I am sending the random bits. So my symbols will also be random, and then that means my AKs are random and depends on the line code as input and the line code itself. Now yt is a pulse amplitude signal. Yes, that we know that yt is a PAM signal. Now depending on the line code, that means AK takes on the value. Say if I have some, if you can allow me to, see if it is something like that, this type of codes. AKs will be either +1 or -1 kind of. Okay. So or not this one. If I take the line code, sorry, this is not line code. Something here, if you just consider, that means that AKs are only some 1 or 0. Sometimes here also AKs are some 1 0 kind of thing. So sometimes it is bipolar, means 1 0 negative is that. So here that means so AK can take the AKs as the symbol values basically subject to some constraint. Now I like to calculate the PSD of yt. So PSD of yt means that means it is the PSD SYF. Basically, if you see, that means PSD of this one is equal to mod of that PF square and into PSD of xt. That means if you see, it is SYF equal to mod of PF square. PF is the Fourier transform of the frequency response of PT mod this one and SXF. So that means this relationship allows us to determine this SYF. That means and the PSD of a line code corresponding to any pulse shape. Now let us make the things little. Let us do certain assumption. Let's take some assumption. Okay. First of all, that I am assuming each pulse has a width of epsilon, which is tending to 0, and the K pulse height, that means that AK is some sort of a area where epsilon and HK is the height, epsilon is width, epsilon is tending to 0, and HK in that case tending to infinity, so that the area is AK is finite, something like that. I am just defining this, and I am calculating some sort of a. So what about this one? This one I am talking about in terms of what is each pulse has width epsilon, means which pulse I am talking about. I am talking about impulse train xt. Please try to understand. Impulse train xt. That means impulse train xt means, you see, that means what I am trying to say, I am saying my thing is that actually this is like this. Okay. This is epsilon and this is hk. Epsilon tending to 0, hk tending to 1, so that each one AK is hk into epsilon. Okay, AK equal to hk into epsilon, epsilon tending to 0 and hk tending to infinity, keeping the product constant. Okay, that means this impulse, this is the pulse train, xt I am talking about. Okay, about this pulse I am just representing by a rectangular. And then I am trying to calculate the autocorrelation. That is, we know but what about the autocorrelation function? The definition of autocorrelation function is some signal, say rectangular pulse train x@t, and it is the tau lag x@t minus tau. You just do minus t by 2 to plus t by 2, some arbitrary t, and take 1 by t and limit t tends to 0. Okay, this is it is defined as autocorrelation function of, say, x@. Okay. Or if you drop that hat, it is xt. Now, also, if you just put in place of minus tau, you will find that r of tau equal to r of minus tau. So that means autocorrelation function is an even function of the lag tau. Okay. And if you just play a little bit when tau is less than epsilon, that means, and I know that AK is epsilon into h, epsilon into hk. Now, if you just do little bit of calculations, then you will find that it is x@t and x@t minus tau. So 2h square term, hk square has come, and it is epsilon minus tau. Let me show that picture. That means I have a pulse like this, say rectangular pulse. Each one is hk. This one is epsilon, so that area is ak. Starting point is k into t. Forget about b. Okay, and I have just x. This is xt. Say x@t. I have shifted a little bit x@t minus tau. I have assumed that tau is less than epsilon. If tau is greater than epsilon, then it will move outside. Okay, tau is epsilon, little bit shift. Now, if I just multiply and integrate it, then what will happen? Hk square into epsilon minus tau. Then, because this terms will be 0. Okay, because I have this term dt term. So now, because outside this interval you have your hk value is 0, so it is sum, and if I take this integration to summation, it will come that this portion is constant. Okay, so hk square epsilon minus tau, and just I am taking summation over k and just 1 by t. And if you just do little bit of modifications, if hk equal to ak by epsilon, then hk, if I just do hk equal to ak by epsilon, and after some time, and this t I am just writing, this 1 by t I am writing as this t, I am writing n into some symbol duration, say some into tb. Okay, this please remember this t is a generic t, that means minus t by 2 to plus t by 2, just a generic variable. So what I'm trying to do this whole time, because see, try to understand. This is TB or TS, whatever you say. That means this is my KTB, this is K plus 1 TB, this duration is TB. I am saying that whole time, that is I am writing as n into TB. That means n number of pulses are there, and I am just doing just in place of T, I am writing n into TB. And finally, what I am doing, that summation. So if I do like this from here, what it will come? That means 1 by epsilon 1 minus tau by epsilon. Okay, then summation. Then T is n into TB. Okay, so I am just writing TB. Okay, then I have a summation over AK square. Okay, and there's a n term 1 by n. Okay, now that 1 by n, and I have a limit. Sorry, that's a limit over n tends to infinity, because t tends to infinity. I am saying TB is fixed. T tends to infinity means n tends to infinity. Okay. Now, what I am doing, this term, that limit n tends to infinity. So I am doing what? That 1 by epsilon TB, 1 minus tau by epsilon, summation 1 by n a AK square. This term I am just defining as R0. Okay, this is, so that means R0 by epsilon TB 1 minus tau by epsilon. So that means what is R0? R0 is in terms of line codes, actually symbols. I am just writing that. Okay, so that means rather I am just I can. So R0 is basically okay. Now that if you so basically they have done this. R0 is this one. Okay. Now little bit of, say, if I take that some AK bar square of it. Okay. Now similarly that the Rx tau basically, so if I just see from equation 7.3 means what? Now that R0 by epsilon TB 1 minus tau by epsilon. This is your autocorrelation function. So this is your autocorrelation function. Okay, where mod tau less than epsilon. Now what is the meaning of this one? What is the meaning of this one? If I just do the plot, then you see that means when I have a convolution of same pulse with same one, that means I will have a so when I am doing a convolution, that means with HK at KTB, so I will have this triangle. Okay, that triangle, if you see that triangle, I am getting the expression of triangle in. Please remember this is in terms of tau, and so that means I have that HK, when HK is, say when HK is coming like this, then no overlap. After some time there is some overlap. At some point this is the maximum overlap. Then again it is going back. then final it is coming out. So, and you are checking the overlap area, so you will get a triangle kind. And finally, when your hk when your tau is greater than epsilon, what will happen? After some time, this hk will come here. That means no overlap. So you are getting a 0. After that, you are basically overlap with hk plus 1. For that, you are getting some sort of a r1 by epsilon. And if you do the same analysis, that means you will get this, and you will find that r1 will be some limit t tends to infinity tb by rather 1 by n ak plus 1. Okay. Something that you see previous one we got limit n tends to infinity 1 by n ak square. Here it is ak plus 1. In that way, we are getting r1. So similarly, rn will get, that means limit n tends to infinity 1 by n ak plus n. That means that, say, this pulse is basically overlapping with this pulse. Say some n1 and n tends to infinity. We will see that n tends to infinity. So in that way, how will you calculate the autocorrelation? The autocorrelation, if I just do these things R1 to R10, then that means this is the discrete these terms. This is called the discrete autocorrelation function of the line code symbols AKs. Okay. That means R1, R2, R3 in that way. This is my discrete autocorrelation that you have already studied in signals and networks class. Now, from there, actually, what we are defining that to find the Rx tau, we are now defining epsilon tends to 0. As epsilon tends to 0, your triangular pulse, if you see that if your epsilon tends to 0, this step epsilon tends to 0, then what will happen? Your triangular pulse will be like this. Okay. Now, it will be, and what about the area? This area is, what about the area of the triangle? Half into base into height, half into 2 into epsilon r0 by epsilon some tb. So r0 by tb. Yes, it is coming. That means it is r0 by tb. Each one. Okay. Now I have my. So that means what is this? The autocorrelation r. Now if I take the autocorrelation of the signal x, that means it is 1 by tb n minus infinity to infinity rn delta tau minus n tb. Okay. So this one, that means this is my autocorrelation function of the input signal x. Okay. So what is my input signal? If you can remember, this was my input signal, and these input signals autocorrelation I am calculating. Why I am calculating autocorrelation? Because finally I have to calculate the power spectral density, and power spectral density is the Fourier transform of the autocorrelation function. Okay, so I have got the autocorrelation function. Autocorrelation function is this. Okay, now with this autocorrelation, I am calculating the power spectral density of x, which is just 1 by tb n minus infinity to infinity at different rns e to the power minus omega. Just if I take the Fourier transform of this one, okay, e to the power minus j in 2 pi ft. Now, and I know that rn equal to minus rn. So if I do, so that means if I take the all symmetric terms, then I will get a cos term and there's some sort of r0 term for n equal to 0. And these SXF, and then I have a filter impulse response is PT. Okay, so I have got SXF. So what I will get? SYF. SYF is the mod PF square into SXF. SXF is 1 by TB, this expression. Okay, summation. So that means that output, the PSD of a line code is fully characterized by its Rn. Okay, so that means the line code means that X, that is fully characterized by PSD is fully characterized by Rn, and that the the output, that means Rn, R0 and the pulse shaping function. So with this, you can completely characterize the PSD of the line code SYF. Okay. Now, say for different types. So is it clear? So that means if I choose the line codes properly, line codes means what is Rn? Rn basically in terms of AK and AK plus N. Basically summation over AK and AK plus N. Okay, if I choose the line code properly, then that means if I choose the AKs, then I can choose the Rn and R0, and if I choose the pulse shaping function or PF, some say pulse function, then my output PSD is actually characterized. Say in case of polar signal. Say in polar signaling, 1 is transmitted by a pulse PT and 0 is represented by a pulse minus PT. Now AK is equally likely, say AK is the symbol. I can take 1 and minus 1. Okay, so AK square is always 1. So what is my R0? R0 is, if you can remember, summation AK square by n limited tends to infinity. So what is that? There are n pulses, I am assuming. Okay, so AK square is 1. Okay, AK square is 1. So that means R0 is 1. Okay. Now if I take, what about R1? R1 is AK. If you remember, AK and AK plus 1. So that means AK means minus 1 plus 1 and AK plus 1 is minus 1 plus 1. So that means product AK and AK plus 1, minus 1 plus 1, plus 1 minus 1 minus 1. So these 4 combinations, and with that these 4 combinations, if you half of the time it will be these 2 combinations, half of the time it will have these 2 combinations. So n by 2 1, n by 2 minus 1. Finally R1 is 0. So arguing in this way, if I just do this, Rn will also be 0 for n greater than equal to 1. Okay. So from that, if you just do this, so that means your Rx, so you have only R0 term. Okay. So if you have only R0 term means SXF will be R0 by TB. So that means R0 is 1. So that means 1 by TB, and it is and R0 by TB. Then what is R0 by TB, and it is not PS, it is the PS square. Now what is R0? R0 is 1 by TB. Okay. Now, for the sake of comparison of various schemes, we shall consider a specific pulse shape. Say PT is now a rectangular pulse with TB by 2. Okay. So now that is half with rectangular pulse. So it is I can represent as T by TB by 2 kind of. And then if you play a little bit with and with this, if you calculate, that means that if you have the pulse of, if you have a PT is a rectangular pulse with TB by 2, that means this is TB by 2, and rest of the whole thing is TB kind. So if you play with it, if you have a rectangular pulse, what is the frequency response? Frequency response will be sync. I have a sync, so that means sync. So it is coming as a sync, and finally SYF, that means the output power spectral density will be related to this TB and let's say TB with the symbol duration. So that means you see that polar signal has most of its power concentrated in lower frequencies. So the spectrum becomes very small as frequency increases, but never becomes totally zero above a certain frequency. So that means these polar one we don't because if you remember that something like that. So that means here f equal to f, here it is 0. So you have a lot of low frequency content, so which we don't like. Okay. So similarly for so we can or we have plotted this actually, that is why. So you see that at the then what is my essential bandwidth? So that means I have a lot of in this zone, lot of energy is present. So which one we don't like actually, because the coupling is difficult. So this is the problem of a polar signal. Now I want to do some sort of a DC null in the PSD by pulse shaping. So that means for polar signal, now try to understand that. Very important point is the pulse shaping. That means I want to do this. I want to make some sort of a, say I don't want like this, say I want something, my pulse, I want to shape like this. And then okay, something like that. This is called pulse shape. So now that this pulse shape shaping we will discuss maybe tomorrow. Okay. So till now, please try to read this portion. Okay. So I think that tomorrow I will take lecture and this portion, because now we are really entering into that core communication portion. Please read this book, Bipolar actually. Okay, so today I am just stopping here because pulse shaping I need some more time, or if you hello.
Yes sir, can you just explain me how that PF function came?
Pardon? How?
Sir, the transform of the rectangular pulse.
Means you are talking about this one? You are talking about this
yes,
one?
Sir.
Okay. So
yes,
forget about this one. Say I have a, forget about this one. Say I have a something like this. I have a signal. Okay. Where I have 0, capital T, and minus T. This is 1. This is 1. This is T. This is some X. Okay. Is it okay?
Yes.
Now I have to calculate x of f. Can I calculate by Fourier transform? But what will I do? Minus t to plus t xt e to the power minus j 2 pi ft. Okay. So xt is 1. So I will remove this. Now, if I do these things, if I just integrate minus t to the power minus j 2 pi ft. So what will come? From there you will find that you will get a same type of. Okay. Just for the time being, you remember, if I have a rectangular pulse, okay, some 0 and this is t, then I will have a sync type of things, where it will be, this one will be 1 by 2. And what about the area? Say this area is, say, this is t, this is some area, height is h. So area is h into 2t. Okay, so this length, this one will be h into 2t. Okay. You just do these things, it will come. Okay. And for Lathi book, actually, you see that how they have defined this pi function. Actually, pi is a box function. Box function is this type of function. So I have forgot that how they have defined this one. But basic idea is that you have a rectangular pulse. They have defined in this way. Nothing great about it. They are writing it in a cryptic way. So it is at the first page, most probably it is given that probably it is given. Rectangular function. Yes, right. Properties of Fourier transform. Okay, so this one, as per their notation, just let me unnecessary confusion. This function, as per Lathi book, the notation is TV by 2 means width is TV by 2. Okay. So from here to here, it is TV by 2. Okay. Now, if you just do the Fourier transform, okay. So now, for just I'm showing you some other one. If I do the Fourier transform of a signal, something like this, okay, where it is some tau by 2, 2 minus tau by 2, okay, and this is 1. If I take the Fourier transform, you will have a something like that same function, okay, where I told that whatever you have this side, this one is 1 by 2 of that one, means tau. That is, basically you will have 1 by tau. If this is your GT, they write GT as in their notation pi of T by tau, means T by width. In this way they write. These are. And what is about G of F? This is your F. This is G of T. G of F is basically tau sync you understand, I think, sin x by x. T pi f tau. Pi f tau. Okay. Now in this case, what they have done, if my Please try to understand. I have to do the PT. So PT is your. Now what is my PT? PT equal to pi T by 2. Okay. So now in place of tau, you put TB by 2. TB by 2 sinc of pi f TB by 2. This one same. Tau TB by 2 sinc. Sinc means sine of this divided by that. Sinc pi f TB by 2. Yes, TB by 2 sinc pi f TB by 2. Okay, this one. So you are getting now. This is please try to understand. This is just a Fourier transform. This is just a Fourier transform. Now, if you see, that means why I have what is this one? Just 1 minute. So now when FTB by 2, when FTB by 2 equal to 1. Okay. Then what about this term? This will be sinc pi. That means sin pi by something sin pi by pi. Sin pi by pi means it is 0. Okay. So that means when f equal to 2 by TB, when f equal to 2 by TB, I have a zero percent. Okay. F equal to 2 by T. This is their problem is y. Oh. Now, so this is about PF, and then SYF is a sinc square. Why sinc square? Oh, that is SYF is the mod PF square. Mod PF square means you have a sinc square. Now, if I have a sinc square, then actually see, for sinc you have some negative law, but for sinc square you don't have negative law, so you will have these things. Are you getting my point? So is it clear? Anyway,
yes,
thank you. So I have calculated PF, but I have to calculate SYF. SYF is some mod PF square into T. But PF is mod means it is first of all it is real, so mod does not mean anything. So I will do PF square, that means TB square by 4 sinc square. Okay, TB, but I have another by TB, so TB 1 square has gone. So that means SYF is some constant into sinc square. So that they have done. So it is like this, the negative lobe has gone. So this is the output signal's power spectral density. Because when it is a random signal, see why is a random? If you remember, because in the line code you are sending randomly the signals. So this one will be random. So just like that, you cannot take normal Fourier transform. You have the normal Fourier transform will give you the frequency response. But when you are randomly sending things, then actually in place of Fourier transform on the stochastic part, we do the power spectral density. Okay, as simple as that. So we have calculated the power spectral density here. This is my SYF. Now I like to shape this pulse by choosing the PT, so that by choosing the PF. Now I am saying instead of rectangular pulse, I will choose some other pulse so that I will have some good things. So that means when PTI will change, PF will be changed. PF change means here some SYF will be changed. Okay. So that is called pulse shaping. That is called pulse shaping. Okay. So we'll discuss this tomorrow. So thank you very much.